Alright, here's 7-3 day 1. And we are just making a pretty simple switch to section 3. It's time to start talking about means. Section 2 was just on proportions. And now it's time to start addressing means. So what I have here is a topic that I want to get into a lot the next couple of days. I have a population distribution right here. It's for professional baseball players and the number of stolen bases. Okay? It has a very extreme right skew, and that's why I chose it. You can see on average, players don't steal many bases. It looks to be centered, honestly, at about 2 or 3. Okay? There are a handful of players that steal lots of bases, right? You can see there's somebody, I cut it off at 20, but the best in the league was up at 70. So there are some outliers on the high side, a handful of very fast players that steal lots of bases, and it leads to an extreme right skew. Okay? Here is a sampling distribution with sample size 45. Okay? And it does mention up here that this population has data on 1,341 players. Okay? So we took a sample of 45, well within the 10% condition, by the way. And we see that it's centered at about 3. But you can see, even though we had an extreme right skew to our population, the sampling distribution looks approximately normal. Okay? Now, I'm not going to formally define this until tomorrow, but I just want to get it out there that when you're looking for this normal condition, I just want to get the number kind of on your radar to get you thinking about it. It's 30. If you want to use a normal approximation. Okay? So even if your population has the craziest distribution ever, if you're looking at a sampling distribution of size at least 30, things in the sampling distribution are going to start to look really normal. Okay. Make sure to read up on the context on this one. Talk about number of movies viewed per year. The only thing that would prevent me from saying that it's centered at the population mean is bias, and it said they did an SRS if n equals 100, so I'm going to assume that we don't have any, and I'll center my sampling distribution at 19.3. Different formula for the standard deviation. Sigma right here is your population standard deviation. And a sample size, as always. I have both these numbers that said it varied from one student to the next on average by 15.8 movies. I got to divide that by the square root of 100. Notice I still addressed the 10% condition. Okay, because to use that formula, this works for sampling distribution, so I need to stay within 10%, but as long as my population has at least 1,000 students, it's good to go. Okay, so really the new thing there is for the standard deviation formula, it's different from a proportion. Okay, so a couple things to notice that have been different. different condition for a normal approximation, different standard deviation formula. All right. Essentially what's going on in this problem is this. From comparing the population, you can really think about it like you're taking a sample of 1. Okay? And then over here, n is 10. But you could take the exact same approach to either problem. Okay? Now you might be thinking in the back of your mind, wait a minute, you said if we're going to use a normal approximation, n had to be 30, like you said that 2 slides ago. Here I don't have to worry about it because the population I'm working with was normal. If you were thinking back to that stolen basis problem, I had to hit that, I needed a sample over 30 because the population was a right skew. Okay, if the population is known to be normal, you can really use whatever sample size you want, and you can still use the normal approximation. Okay, so as far as just kind of thinking about this, which one would we be more likely to get a single jar that weighs less than 16 ounces or an average of 10? It is an average of 10, okay, because there's going to be less variability from 16.1 ounces. Okay, if you're just taking a single jar, the results could vary. Right? You might get a really, really light one. If you get that same light one from a sample of 10, you've got 9 others that will probably average it out and bring it closer to 16.1. So that's one way you could think about it. The other way is to just say, fine, we'll go do a normal approximation. This is if I selected 1. Told me in the problem that sigma was 0.15. We are right here. You can go normal CDF that, and you get about 0.25. Okay, so 1 in 4 chance if you select 1 jar that it would weigh less than 16 ounces. Over here, I'm doing the same thing. There's my normal curve. Mean is 16.1. Sigma is now going to be 0.15 over the square root of 10, which is 0.047. Like we said, less variability. If you take an average of 10, you're probably going to get something that's closer to 16.1 than if you just selected 1. Our location is the same. And you go right back to your normal CDF, and the only thing that you're going to change is sigma. It's going to go from 0.15 to 0.047. And sure enough, it dramatically decreases the odds that we would get an average of 10 less than 16 ounces. It went from like 25% chance if we took 1 to about 1.67% if we did that average weight from 10 jars. All right, once again on this one, told us the population was normal. Okay, so you can see down here, we are going to work with an SRS of 6. That's okay. Right, we know the population's normal. It's worth repeating on that very first one. And again, we'll see it in the lesson tomorrow. We're really concerned with 30 if our population is known not to be normal, or if we just don't know what the shape is. Okay? This is normal. Mean is 266. Sigma is 16. And our location would be right here at x equals 270. What percentage of pregnancies are going over 270 days? And it would be about 40. Okay, it's another normal CDF. You're going to start to see that we come back to using that very, very frequently. All right, so now we're talking about the sampling distribution, because that calculation above wasn't. That was for the population. Okay, that distribution included everybody. Right? I did the same thing on the example with the jars of, it was either peanuts or peanut butter. Peanuts. The first calculation we did was for the population, and now, just like on that one, I'm switching over to a sampling distribution. For my mean, I'm going to use 266, right? Now to explain, all I have to say is we should be centered at the parameter assuming no bias. So I do that. We have an SRS of 6. All right, so I think I can trust that in repeated samples we should be centered right at about 266. Okay. Sigma sub x bar would be 16 over square root 6, which is 6.53 days. Look what happens to the variation again. That first one we did was if we randomly selected one woman. Now we're selecting 6 and take the average, and our standard deviation went from 16 down to 6.5. Verifying my 10% condition. To use that, I have to have a population of at least 60 pregnant women. Seems like a very obvious foregone conclusion that there's probably dramatically more than that. All right, so same calculation, and we saw from the previous slide, again with the peanuts, that this probability should be a lot smaller. We saw it was 40% in number 1. But again, go normal CDF, and the only thing that you would change is sigma needs to get switched from 16 to 6.53, and you would see that the probability of getting a sample of 6 to get an average over 270 would go down to 0.27.